looking at the energy equation, which is basically applying the first law of thermodynamics to our control volume. So let's draw a system out that we're going to take a look at. And so it's going to be a piping system because this is what we're going to be applying all of our things to. So we are going to have a pump and a turbine in our piping system. Let's draw that little trapezoid a little bit better. And then I will have a pipe that connects from the outside to the pump. And we'll have one that connects to the turbine. And then we'll have a pipe. And it really doesn't matter what this pipe looks like. It could have a bunch of curly cues in it. Is that pipe there got fatter? It really doesn't matter, because we're going to do our control volume analysis of this piping system. So let's draw our control volume around it. And it's basically, I am just encapsulating my piping systems. So I have one input and one output into that system, coming in here at the in, coming here at the out. Now let's take a look at the energies that are coming into and out of this system, because we do want to do a control volume analysis. First thing I do want to point out, gravity is going to be operating in this direction. So I do have some fluid that's going to be coming in. It's going to have some m dot, mass flow rates coming in and coming out. And it's bringing energy into the system. What kind of energy is it bringing in? Well, it's going to be bringing in internal energy. So our internal energy, U, that's all based on temperature. We're going to be bringing in boundary work, which is denoted by our pressure. We're going to be bringing in velocity. So we're going to have that kinetic energy coming in. And we're also going to have potential energy coming in, which we will call Z. And so actually U is kind of based on temperature. So let's just call it temperature, because then we can work that property out. So that's all this energy that's coming into our system. What do we have coming out of the system? All the same stuff. So we've got T2, P2, V2, and Z2. So this is all of our energy coming out of the system with the fluid. What other kinds of energies do we have coming in and out of the system? Well, I've got a pump, so I'm putting some work into the pump. I have a turbine. I'm extracting some work out of the turbine. And the last two things that I have is I do have some kind of energy, some heat energy that's coming from the surroundings that are bleeding into the system. And this could also be energy going the other way, going from the piping system, bleeding out into the surroundings, but it doesn't really matter because it's just a sign change at that point. And so the last thing I do have is I do have energy that I'm losing in the system due to frictional losses, the actual fluid moving through the pipe. And so we're going to call that Q dot loss. And so those are all of the frictional losses, because if you think about it, how does friction express itself when it gets burned up against something? It heats up. So anything that's rubbing against each other will start to heat up. So we've done all this, and the question is why? Well, let's look at the energy equation for first law of thermodynamics. And what does that tell me? Well, that tells me that any energy coming into a system has to minus whatever energy is coming out of the system is going to equal the change of energy in the system. So E system. So we're going to be making some assumptions through this. So let's start with our first one. I'll put them over here for now. Well, I want to assume a steady flow. So if I assume a steady flow, that means that ddt becomes 0. This part of the equation will drop out. And so I'm left with the energy in minus the energy out, or it has to equal the energy out. So the energy is going to be balanced. So let's look at our little picture that we just drew and what kind of energy in do we have. Well, I have the internal energy, boundary work, kinetic, and potential energy. And that's all going to be coming in with a mass flow rate that's going to bring it in. So what we have, we have the mass flow rate coming in. So we have the internal energy. Now that is not U times T1. That's U as a function of T1. Our boundary energy is pressure over gamma. V1 squared over 2 is our kinetic energy. Finally, our potential energy is GZ1. On the inside, we also have, well, that Qn, whatever heat's bleeding from the system to the surroundings. And then we're also putting work of the pump in. So this is all of my energy in. What is that going to equal? Well, that's going to equal my energy out. Now, the first thing is the energy that's being carried out by the fluid is going to be the same as coming in. So U as a function of T2 plus, I'm sorry, I wrote that wrong. Pressure 2 over gamma plus V2 squared over 2 plus GZ2. So once again, my internal energy, my boundary work, kinetic energy, potential energy. What else is coming out of the system? Well, I have whatever work of my turbine is coming out, and then whatever I'm losing due to frictional effects. This is a big equation, so we're going to make some assumptions to make it a little bit easier to deal with. So the second assumption I'm going to make is I'm going to assume that I have a constant temperature. So basically whatever temperature the fluid's coming in, I'm assuming it's going to be coming out at basically the same temperature. But that also means that I'm assuming that I'm not either shedding heat to the surroundings or bringing in heat from the surroundings. So because of assumption 2, let me change my color here because I'm going to knock some stuff out. Because of assumption 2, let me write the 2 there to denote that, Q in falls out. Now also, since this is a big additive equation, we're just adding things together, well, I know that I'm going to have U as a function of T1, U as a function of T2. Well, if T1 and T2 are the same, those terms are going to be the same, so I can subtract that from both sides, and both of these guys are going to fall out because of assumption 2. Q loss does not fall out, because Q loss isn't a temperature thing, it's expressing heat from the friction, so we're going to leave that in with our equations. So let's change back to the other color. And so now I also want to assume not just a constant temperature flow, I want to assume a incompressible flow. So I have a constant density. And because I have a constant density, and since the density is not going to be able to change, now I will be able to multiply through by things. So just remember, m dot is rho q, because it's rho VA, so rho q. And now that now that rho is the same, I will be able to divide all the terms through. So what I want to do on both of these sides is I'm going to take each side of the equation, and I'm going to make a little room there. I'm going to multiply through by 1 over rho g q. And I'm going to do that to this other side too. Multiply this by rho g q. And I'm going to do that to put the equation in a slightly different form. So the important thing to note is when the fluid part gets divided by the rho GQ, well, rho Q will knock out the m dot, and so all I'll be left with is G. So now, once I do that, what I'm left with is pressure over gamma, because density times gravity will give you gamma, plus V1 squared over 2G plus Z1, plus our pump work, so work of the pump divided by rho GQ and that's going to equal all the fluid properties at point 2, Z2, plus the work of the turbine divided by rho GQ plus our Q loss divided by rho GQ. Okay, so now we have this equation here. It's a little bit nicer. We're looking at 9 terms, but I want to make the equation a little bit simpler to write, so we're going to make some new definitions of these 3 terms here. So if I look at the work of the pump divided by rho GQ, if you look at the units for this, that's going to leave us units of a linear measurement, which will be, we'll call a head. And so what we're going to do is we're going to call this the pump input head, or just the pump head, and we're going to define that as H sub P, the head of the pump. We're going to do the same thing with the work of the turbine. It's going to be rho GQ, and that's going to be the turbine head extraction. We will define that as H sub T. Now this Q loss term, which is, remember this is, we're talking about the frictional effects in the fluid. This is going to be called our friction head loss. And we will define that as H sub F. You will also see this as H sub L in some text. I believe the equation, the engineering equation manual has that. So all 3 of these, you look at the units, they're in linear measurements. In fact, if you look at the pressure, that pressure head, because it'll be a linear measurement, we have the velocity head, because if you look at the units, a linear measurement, and Z is just going to be a head rating. That's our hydrodynamic head, a linear measurement. This will be continued in the next video.